And I'm going to start talking to you a little bit about irradiated brown dwarfs with my favorite quote about them, which is extremely useful, which is from Adam Showman, and tells us that irradiated brown dwarfs fill this crucial fourth corner of parameter space between isolated brown dwarfs, who are down here at the bottom, with high interior heat flux and low external irradiation, irradiated exoplanets, who are the reverse even, low interior heat, high external heat, solar system planets sort of sit here at the bottom with low interior and external heat, and my irradiated brown dwarfs sit up here. So they sort of fit nicely within the zoo of planets and brown dwarfs and give us an idea of how we can look at all of them and how they all fit together. Now, the problem with irradiated brown dwarfs in general is that there are not many of them known due to the brown dwarf desert. So brown dwarfs in close orbits around main sequence stars, there are about 19 or 20 known to date. And irritatingly, they have more problems than observing hot Jupiters because they have higher masses, higher gravities, lower scale heights, so you can't even perform transmission spectroscopy on them, which is a little bit annoying. What we can do, however, is observe these systems in their evolved forms. So we take the main sequence star and we let it evolve. It becomes a giant. The envelope encompasses the brown dwarf, which begins to spiral in, and provided it doesn't die a horrible fiery death on the core of the star, we're left with, once the envelope's been ejected, a white dwarf, brown dwarf system. So the brown dwarf orbits the white dwarf with a period of a few hours, down to, I think, the lowest period we have at the moment, 68 minutes. And there are 9 or 10 of these known, so fewer than brown dwarfs around main sequence stars. But because they orbit a white dwarf, we have the massive benefit that we can actually directly observe them. So white dwarfs, as you all know, are small. They're Earth-sized, and they primarily emit in the UV and the optical. And when we get to the infrared, you can begin to see an infrared excess, which is due to the brown dwarf. So this is a genospectrum of an as yet unpublished system, which appears to be an L5 brown dwarf orbiting a 10,000 Kelvin white dwarf, a period of about 2 hours. And the nice thing about these is we can subtract the white dwarf spectra off. White dwarfs, conversely to brown dwarfs and exoplanets, are relatively simple to model. And we can subtract white dwarf models and get left with the brown dwarf spectrum. And then we can analyze this with an isolated brown dwarf. So look at gravity-sensitive indices, look at other indicators of gravity, metallicity, etc. Try and determine if the brown dwarf is inflated due to the heat from the white dwarf. What we can also do with spectra is we can try and determine what's going on in the brown dwarf atmosphere due to emission lines. So if the brown dwarf is significantly heated, and we have about 3 or 4 of these that are at the moment, then we get H-alpha emission. So in this case, your dark line is the trail of the hydrogen line. This is the H-alpha absorption feature. And this crazy line here is your H-alpha emission feature. And this is the night side of the brown dwarf, and this is the day side of the brown dwarf. And you can see we have 2 or 3 where this is possible to determine. So WD137 is the best known of these systems. It's a 114-minute period, and it's a brown dwarf orbiting a 16,500 Kelvin white dwarf. These two are in 70-ish minute orbits, around 25,000 Kelvin white dwarfs. So these are moving exceptionally fast around something that's very, very hot. And as you might expect, if we look at the rest of the spectra, if we have it, then we get all sorts of other emission lines. Now, the thing I think is particularly interesting about this is when we came to look at other emission lines and try and determine what's going on in the brown dwarf atmosphere, it became quite clear that we were not getting the same emission features from all the brown dwarfs, and it was not the most irradiated brown dwarf that was giving us the most emission features, which came as a little bit of a surprise to me. So WD137's well-known object has all of these species in it. This is an L8 dwarf. It's at the end of the L to T transition sequence. The white dwarf, 16,500 Kelvin, 114-minute period. This object with the crazy name only has these emission features. They're both sets of X-shooter spectra. We're not missing any sort of emission features here due to wavelength coverage. It's orbiting a much hotter white dwarf in a much shorter period. We see much less stuff. The main difference is the spectral type of the brown dwarfs. So in EPIC, insert telephone number here, it's an L3 dwarf. It's much more cloudy than the L8, where the clouds have started to disperse in some way. So this I found quite interesting. Those of you who studied clouds may not found that as sort of new as I did. But we then found that of the 10 white dwarf brown dwarf binaries known, there are only 3 that are eclipsing. And this gave us the options, particularly in the infrared, to actually directly detect the dark side of the brown dwarf. These things are tidally locked. And they're about 20th-ish magnitude in the H and the K band. So they are detectable compared to exoplanets, where this generally isn't the case. And I apologize for the slightly ratty data. Our Hawkeye time was not taken in as good as conditions as we'd like. But what we ended up with essentially are brightness temperatures for the day side and the night side. These are the maximum and minimum day and night side temperatures. The average day and night side temperatures have a difference of about 100 Kelvin for this object. However, when we compare that to effective temperatures for the day and the night side, we come out with sort of temperatures of about 13,000, 14,000 Kelvin. Now, this object in particular, STSS 1411, the brown dwarf should be a T-dwarf. We have good masses from radial velocities. We have eclipses, so we know its radius. It's not particularly young. There's nothing particularly weird about it. And it should have an effective temperature of about 800 Kelvin. Now, looking at our light curve modeling and all the other information we've got, there's no way we can bump that temperature up to 1300 Kelvin by simply pouring in heat on the day side. Our light curve models, as I'm sure most of your light curve models have, some sort of absorb parameter that deals with the amount of flux that comes in and whether it gets re-irradiated or circulates around the object. And this is at 80-90%, particularly in the K band. So we physically can't stick any more heat onto this brown dwarf to heat it up to this temperature. So we were left wondering what on earth might be going on. And our suggestion was perhaps that what we see as effectively a day-side, night-side temperature isn't a temperature. It's that we have an artificial flux sort of boosting, if you like, due to the UV irradiation from the white dwarf. So we've got some sort of photochemistry going on here, whether it's something like H3+, whether it's H2 fluorescence, maybe it's something we haven't heard of, we're not sure. But we think this might be happening. Frustration of this object is towards the faint end of what we can do. So getting spectra of it in the infrared isn't really possible at 90th magnitude. This is difficult for us. It's a James Webb weight. But the results we get are similar to what we got for WDO137. So this isn't eclipsing, but we have extremely good light curves in about 5 wave bands, and we can subtract the white dwarf contribution. White dwarfs don't vary in general. So we can subtract the white dwarf contribution and calculate the day and the night side temperature from the reflection effect that we see. And using Jonathan Fortney's models here for irradiated brown dwarfs, we found our best fitting model is the black line at the bottom to the day side points, which are these solid points. The night side points are the big squares down at the bottom here. And the model fit quite well to the data. The model has circulation all the way around the brown dwarf, and it didn't have TIO in it, which was something we were looking at the time. However, you can see these 2 points here. This is the K band. This is 4.5 micron. Again, these are the points here are too bright compared to what they should be for the model. And again, if you were going to look for something like H2 plus or H2 fluorescence, these are the wave bands where you would expect to see it. So again, we're left with the suggestion that the UV from the white dwarf is causing some sort of glow or boosting within these wave bands. And this is my great question at the moment. And unfortunately, I'm left waiting for spectra at 4.5 microns, which is James Webb, until we can actually try and determine what's going on here. Okay, so that's sort of my plug for irradiated brown dwarfs and why they're interesting. How do they fit in with exoplanets? So this is a figure I have reproduced from the work of Komacek et al., and I apologize if I've mispronounced your name there. So these are a bunch of known exoplanets with equilibrium temperature versus this A absorb parameter, which is the brightness temperature on the day minus the night divided by the daytime brightness temperature. And you can see that STS 1411, the eclipsing system, sits quite nicely down here, almost on a nice straight line with everything else. WDO 137 is sort of almost on a line below somewhere, hanging out with HAPP 7b, which is everybody's other favorite weirdo exoplanet. So I've shown this because I think it's interesting to show you that these brown dwarfs are not that different from exoplanets, despite the fact that they have higher masses and slightly different radii. I'm curious to see how this changes when we have better data, smaller error bars, and more points on here. And hopefully more brown dwarfs on here as well. Thank you. Okay, so I'm going to finish up talking about the mass-radius relation for these objects. So this is the irradiated mass-radius relationship, irradiated brown dwarf mass-radius relationship. So mass on the bottom, brown dwarf radius on the side, and these are all the known irradiated brown dwarfs around main sequence stars, and the two where we have actual measured radii around white dwarfs. So the two white dwarf ones are here. Interestingly enough, they sit within the so-called mass gap for these brown dwarfs around main sequence stars. And in fact, most of the brown dwarfs around white dwarfs fall around here within this mass gap. This perhaps isn't massively surprising because if we're looking for them, if we're looking for brown dwarfs around white dwarfs in general, then if they are brighter in the infrared, they are easier for us to see, which tends to mean they're the higher mass, earlier spectral type objects. Okay, so the other thing that's quite interesting to look at this, so we've got, these are the model, Isabelle Barraff's models, so 100 million years, 1 gig a year, 5 gig years, and 10 gig years at the bottom. And brown dwarfs all tend to about the same radius as they age. They cool as they age, so degenerate objects. So these objects would be what a brown dwarf person would sort of refer to as having field gravity in general. None of the stars these planets are around are regarded as young, certainly not 100 million years old. So these are the inflated objects. I believe that one there is Kelt 1b. And pretty much everything else isn't inflated. These two might be, but they have whack and grey error bars. They're Corot objects, and hopefully, I guess, Tess is going to provide more information on these and hopefully better radii constraints. They're interestingly, they're also active. They're two of the only active hosts on this figure. But the other thing you'll notice is that basically the things that are inflated are the low mass objects. They're not the higher mass objects. Okay, so how does this work out when you actually think about the orbits, the host star temperature? How does that help, if at all? Okay, so bear with me on my delightfully colored figure here. So the color, hopefully you can see it, refers to the temperature of the host star. So the small red dots in general are the M dwarfs. The big blue ones are the white dwarfs. And the size of the dot is proportional to the amount of flux the brown dwarf is receiving at the surface. So this takes into account the size of the host star, the temperature of the host star, and the period. So looking at this, you can see that there's quite a few here that are getting a fair amount of irradiation, but this one is getting about the same amount, and that object's not massively inflated. Object orbiting this M dwarf, well, okay, it's got large error bars, but do you believe that's, it's getting a lot less irradiation than everything else that's not inflated. This brown dwarf orbiting the white dwarf is getting a huge amount of irradiation and is not inflated. So it appears to me, looking at this, and I'm willing to be corrected and take input from people on this, that the dominant factor as to whether you can inflate your brown dwarf orbiting a main sequence star is simply the mass of the brown dwarf. It doesn't appear to be hugely correlated to the amount of irradiation you're pumping into that brown dwarf. It's to do with the mass of the brown dwarf itself. Okay, so I'm going to finish up here, and hopefully I've convinced you we can directly observe irradiated brown dwarf atmospheres, and that from admittedly, the two objects we're looking at the moment, there doesn't appear to be a clear link between more UV irradiation and more emission features in the brown dwarf atmosphere, and that a hotter, shorter period doesn't equate more emission lines in the brown dwarf atmosphere, and that more radiation doesn't necessarily indicate more inflation in the brown dwarf either. And it does appear at the moment that in the two brown dwarfs we have data for, UV emission is linked to a brightening in the K-band, although we need more data on more objects. Admittedly, it's a little tricky when you've only got 9 before we can confirm this in more detail. So I will finish there. Thank you very much.
Who got the microphone? The second one. Yeah.
Right, I can.
Okay, so I'll start with the question while we find the other mic. So the case where you were comparing the elements that we see in the brown dwarfs, and you said that the cloudier brown dwarfs show less elements. Is that just because you're masking the spectral features behind clouds, or is it because you're actually sequestering those elements into cloud particles?
Marvelous. To be honest with you, I really don't know. We talked to Christiana Helling a lot about this, and I know she's not here yet because her flight doesn't get in, so she won't be here till about 11. But with WDO137, where we saw that whole range of elements, we suspected there might be some sort of almost like a chromosphere around the brown dwarf, and that was what we were seeing. For EPIC 2122 telephone number, we were less sure. We were surprised we saw much less, but it is a much cloudier object, and I will admit at this point that clouds are not my thing. So to be honest with you, I'm not really sure. There is another object that shows emission, which is a later type. I think it's an L6. And that system also shows evidence of having been polluted by rocky material. So there's been some sort of planetary system there as well. But again, that doesn't show, it doesn't even show the same elements as EPIC 2122. It shows different ones. So at the moment, where I am at is basically we need a lot more of these with a lot more different spectral types and levels of irradiation to really have any sort of idea of being able to say what's going on.
So, Sarah, yeah, you alluded to the photochemistry, and this keeps coming up. So I'd just like to continue this theme. So for the case of the mysterious absent emission lines, I'm just wondering whether the photochemistry itself would just drive the disappearance of the neutrals or the singly ionized species, which are responsible for these. Sodium is very susceptible to ionization, and so it wouldn't surprise me if there's just no neutral sodium available for emission in the D lines. And then related to that, something perhaps you thought about, I haven't wrapped my head around this yet. Dissociation of actually some of the molecules responsible for opacity in these objects, in addition to the issues with clouds. So the titanium vanadium oxides will ionize at some point. And I wonder if that could somehow modulate the temperature structure and the thermal budget, and maybe related to something you've seen in the K-band emission.
Yeah, so that was something we looked into a little bit with WDO137, particularly the titanium oxide, because when we originally looked at the day-side, night-side temperatures, we sort of went, oh, okay, is this a temperature inversion? This is what everybody's been saying should happen in exoplanets. And then we sort of looked at it a little bit more detail. We looked at the models. We looked at the temperature pressure scale heights from Jonathan and Mark's models, and we sort of came to the conclusion that really wasn't likely to be the case for this object here, and that photochemistry was possibly the most likely thing that's going on. I mean, ideally, we need phase result spectroscopy in the K-band at 3.6 and 4.5 microns, but even at, with a 2-hour period and that object's 15th magnitude, that's still really tough to get short enough cadence in your spectroscopy in the infrared to actually get something sensible out of it. It's really, really hard.
Okay, last question, Jane.
Hi, Sarah. Nice to meet you. This may be a naive question, but do you consider, is it possible to have reflected light from these objects? And does that add to your anomalously deep?
So, and I'm willing to be corrected, but when I've talked to people over the horrible static that I'm currently experiencing, the suggestion has been that the reflected light mainly is going to show up in the optical. And I have sent my light curves for WDO137 to Mark Marley at some point last summer, and he was going to have somebody look at that in particular, to look at the reflected light from clouds or anything, whether anything like that's going on. So these things vary at the 1% to 3% level in the optical, and it's almost 30-ish% by the time you get to the K band.
Okay, thanks.
I'm not sure that answered you necessarily, but
no.
Okay.
Actually, I wonder if could I ask you a question? While I'm here, so I was interested in the day side, night side temperature contrast plot. So a parameter that's relevant for irradiated brown dwarfs, that's not so much an issue for hot Jupiters, is the ratio of the flux coming out of the interior to the illumination. I was just wondering, to what extent can you estimate the flux coming out of the interior from the age and from the equilibrium temperature, or do we just not know that?
I have no idea, but I might pick on Jonathan and see if Jonathan would like to answer that instead.
I mean, I don't remember off the top of my head, but yeah, if we have a math and a decent age, then you should be able to constrain the flux from the interior pretty well.
So they're not my model. Yeah. Yeah, so you could if we take the spectral type at face value, if you like, and use albedo, etc., for non-irradiated systems, then yeah, I guess you could work that back and look into it. I will have a think about that.
Okay, thanks so much, Sarah.